As we start our new unit on analytic trig, I'd like to do an opener here with a right triangle. So let's say we have a right triangle with one of the acute angles labeled theta, and the legs are A and B, and the hypotenuse has length C. So I'd like you to simplify sine squared plus cosine squared in terms of A, B, and C. All right, that sounds simple enough. Let's see what happens. So the sine of theta is opposite over hypotenuse, so that's A over C. So the sine squared will be A over C quantity squared. The cosine of theta, likewise, that's adjacent over hypotenuse, so we have B over C, and that's squared as well. So let's simplify this. So we wind up with A squared over C squared plus B squared over C squared. And we can combine these fractions. They already have a common denominator. So that becomes A squared plus B squared all over C squared. But from this right triangle in the Pythagorean theorem, we know that A squared plus B squared equals C squared. So I can replace the numerator with C squared. And so I get C squared over C squared, which equals 1. So in terms of this picture here, the sine squared plus cosine squared equals simply 1. Let's look at another one. It's a good idea to try these first and then see how you did. Let's simplify the tangent squared theta plus 1 by using sine and cosine. All right, so we know the tangent is sine over cosine. So I'm going to replace tangent with sine over cosine. And so the tangent squared will be sine squared over cosine squared. Now in order to add 1 to this, we need to turn it into a fraction so it has a common denominator. So I'll multiply the 1 by cosine squared over cosine squared. Remember, with expressions we're allowed to multiply by a form of 1. That doesn't change the value of the expression. Now I can combine these, and I'm going to get, running out of room here, I'm going to get sine squared of theta plus cosine squared of theta all over cosine squared of theta. But from the previous example, we know sine squared plus cosine squared equals 1. So this becomes 1 over cosine squared of theta. And we know 1 over the cosine squared is the same as the secant squared of theta. So tangent squared plus 1 is equal to secant squared. All right, let's try one more. Let's try cotangent squared plus 1 by using sine and cosine again. So similar idea, you probably already know where this is going to go. Cotangent is cosine over sine. So when we square it, we'll get cosine squared over sine squared. And then we're going to add 1. So let's have a common denominator. Let's change 1 to be sine squared over sine squared, so that we can combine these two fractions. And so with the common denominator, we add the numerators, and we have cosine squared of theta plus sine squared of theta all over sine squared. But from our first example, we know the numerator, cosine squared plus sine squared, is equal to 1. So we have 1 over sine squared of theta. And 1 over the sine squared is the cosecant squared. So cotangent squared plus 1 is cosecant squared. So these three examples lead us to the important Pythagorean identities, which help us manipulate trigonometric expressions. So we know the sine squared of an angle plus the cosine squared of that same angle is equal to 1. The tangent squared plus 1 is equal to the secant squared, and the cotangent squared plus 1 is cosecant squared. So those are going to be worthwhile remembering. As you work through problems, we'll use these so much, especially the first two, that you won't have any trouble remembering those. So let's look at several examples. I'd like to simplify the sine of x times the cosine squared of x minus the sine of x. Now, first thing I want you to notice is this is an expression, not an equation. And the only thing you can do with an expression is to do some legal algebraic manipulations that we've learned in the past, like factoring, multiplying by forms of 1. And so we want to look at this and think, okay, what can I do with this? I see that I have two terms, and I could factor a sine of x out of those. So let's factor out a sine of x and see what we have. We're left with a cosine squared of x minus 1. Now, cosine squared of x minus 1, that should ring a bell. That reminds me of the first Pythagorean identity. And if I rearrange that equation, if I move the sine over to the right side, and I subtract the 1 over to the left side, then cosine squared minus 1 is equal to negative sine squared. So I can replace my brackets with a negative sine squared. And now I can multiply those out, and I get negative sine to the third power of x. So I've simplified my original expression down to just negative sine cubed. There's not a certain set of rules that I could list for you and say, okay, when you have this, you do this. It takes practice. It's more of an art form. So the more you practice, the better you'll get at it. And sometimes you'll go down, you'll try something and it won't work, and then you'll have to back up and try something else. And through experience, you'll start to see several steps ahead before you dive into a problem. All right, let's look at this one. Show that the cosecant squared of x minus the cotangent of x minus 3 is equivalent to the quantity cotangent of x minus 2 times the quantity cotangent of x plus 1. So, what do we do with this? Well, there's a couple things we should notice. First of all, they want us to take this original expression and write it in factored form. But notice in the factored form, I'm only dealing with cotangents. In the original, I have a cotangent here, but I have a cosecant squared. So that doesn't seem to fit. So maybe I can use one of those Pythagorean identities to replace my cosecant squared. So I'm going to go back up here and say, oh yeah, that's right. Cosecant squared is equal to cotangent squared plus 1. So I'm going to go back here. And remember, I'm starting with this, and I'll write it again. I'm starting with cosecant squared of x minus cotangent of x minus 3. That expression. So let me replace cosecant squared with cotangent squared plus 1. And then I have minus a cotangent of x minus 3. I have some constants that I can combine, so let me write that. So I have a cotangent squared of x minus a cotangent of x minus 2. Now what do we do? Well, when you look at that, hopefully you think of that in a more general sense as a squared minus a minus 2. And if I gave that to you, I'm sure everybody could factor that. And we know that's where we're headed because we have to factor it, because that's what we're trying to get. And if I factor this, it would be a minus 2 times a plus 1. But instead of a, we have a cotangent, but it's still the same idea. So I'm going to have cotangent of x minus 2 times cotangent of x plus 1. And that's exactly what they wanted me to change it to. And there you have it. All right, let's look at a few more examples. And as usual, I would probably pause, try and work this out, spend a couple of minutes, and like I say, sometimes you're going to go down the wrong road and you'll get to a dead end, and then you'll have to back up and try something else. But it's that experience that helps you get better at this, not just watching somebody else do it. Okay, let's simplify sine of t plus cotangent of t times cosine of t. Well, let's see. There's nothing we could factor out like in that first example. one thing I do notice that I have 3 different functions. So maybe I can try and condense this down to have 1 or 2 functions instead of 3. I also noticed that there's no squared on any of these, so I can't use the Pythagorean identity, at least not yet, because all those dealt with cosine squared or sine squared or tangent squared. So let's start with the cotangent, because I can write that as sines and cosines. So I've got sine of t plus the cotangent is the cosine over the sine, and then times another cosine. If you want, you can write that as cosine over 1. And if I'm going to add these together, I'm going to need a common denominator. So that means that I'm going to have to multiply the first term, sine of t, by sine of t over sine of t. And then I'll have a common denominator, and I can combine those. So the first term, I'm going to have sine squared over sine. And then I'm going to add to that, the second one, I'll have cosine squared over sine. So I've already combined the 2 fractions with that common denominator of sine of t. And now I recognize the numerator. Sine squared plus cosine squared is equal to 1. So I can change that to 1, and I have 1 over the sine of t, which is just equal to, let's go over here, which is equal to the cosecant of t. So all this stuff simplifies down to just cosecant of t. All right, let's look at a different type of problem. Rewrite 1 over 1 plus sine of y so it's not in fractional form. So we have to think back to algebra, and when did we deal with stuff that had fractions? And so you may recall sometimes when we were trying to get rid of square roots in the denominator, we'd multiply by the conjugate. Well, let's try that here. Let's multiply this by 1 minus sine of y over 1 minus sine of y. How would you know to do that? Experience. So like I said, you have to practice, you have to try things. And remember, this is just an expression, so the only thing I'm allowed to do is multiply by forms of 1. All right, so when I multiply this out, in the numerator I'm going to get 1 minus sine of y. But look what happens in the denominator. It's going to be the difference of 2 squares, and when I multiply those 2 binomials, I'm going to wind up with 1 minus sine squared of y. Now if you don't see that, then go ahead and multiply this times this, multiply the first and the last and the inner and the outer, and you'll see that the middle terms are going to cancel. So let me get rid of those. There, and there. And you'll wind up with 1 minus sine squared in the denominator. Now, what's 1 minus sine squared? Let's go back here, and let's look at this first Pythagorean identity. And if I move the sine squared to the other side, I'm going to have cosine squared is equal to 1 minus sine squared. So I'm going to replace in my problem the 1 minus sine squared with cosine squared. So now I have 1 minus sine of y over cosine squared of y. Now you're thinking, well, that's still a fraction. How does that help me? Well, I could split this up into 2 separate fractions. So I could write this as 1 over cosine squared of y. I think you know what we're going to do with that. And then minus sine of y over cosine squared of y. All right, so let's take that first fraction. 1 over cosine squared is secant squared. No more fraction. That's good. Now what about the second one? I have a sine over a cosine squared. maybe if I split that up, a sine of y over cosine y times 1 over another cosine of y, that's equivalent to the fraction sine over cosine squared. But splitting it up that way, now I can take that first fraction, sine over cosine, and that's tangent, and 1 over the cosine, that's secant. So now I've rewritten my expression so it does not contain any fractions. All right, let's try one last one. And this is a technique that's very useful later on in calculus when you start learning about techniques of integration. But we don't have to worry about that now. Let's worry about the algebra part of this. Use the substitution x is equal to 2 tangent of theta. So they're telling you substitute in 2 tangent of theta for x to write the expression the square root of 4 plus x squared as a trigonometric function of theta. So I'm going to take that square root of 4 plus x squared, and I'm going to replace x with 2 tangent theta. So when I square it, I'm going to get 4 tangent squared theta. Now what do I do? Well, we're adding stuff, so I could factor a 4 out of the 2 terms, and I'll have 1 plus tangent squared, and all of a sudden, ding, 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 that looks familiar. Now the square root of 4 is 2, so I can bring that out of the square root. 1 plus tangent squared, that's one of our Pythagorean identities, that's equal to secant squared. Now what's the square root of secant squared? You're probably thinking, well, what about, shouldn't I write absolute value of secant? And I don't have to because of this condition they gave me in the problem. Theta's in the first quadrant, so I know the secant is going to be positive. So final answer, that square root of 4 plus x squared is going to be equivalent to 2 secant theta when I do the substitution that x is equal to 2 tan theta. And like I say, later on when you're dealing with integrals, you'll learn that this can be very helpful. Okay, so your assignment is not out of the text, it's worksheet 5.1.